It's been not only an honor, but a pleasure to be here. And so, where's Mark? There he is. I want to thank all my hosts, especially Mark, who's been such a great host. And we even have a dean here. And I would like to thank, aren't you a dean? Associate dean, okay. And I want to thank all of you, for your enthusiasm and good questions, and it's very inspiring. In fact, I was thinking today, we're such good friends that I should just come in shorts and a t-shirt. And I actually brought a t-shirt for the occasion because I had seen that this year UVA is the #1 party school. So what are you doing here? And of course the University of Chicago, does anyone know our motto? Where fun goes to die. I have a t-shirt to prove it, but I decided not to, again, I'm very honored by being invited to give these lectures, and so I thought I would I didn't want to, break with my tradition for the first 2 days and risk something bad happening, so I did not wear that t-shirt, but I worked in the joke. Okay, so we're really going to have fun today. And it sort of reminds me of, 3 lectures and Charlie Parker, first you learn your acts, then you learn your music, and then you just play. So today we're just going to play, and it allows me to do some things that I normally don't do, which was this limits to cosmology. And so at the very end, I get to tell you about what I think may be the limits to cosmology, and I get to talk about a paper that I wrote in 1999 called Limits to Our Arrogance, because that'll be the lead-in for it. But first, let's talk a little bit about those big mysteries. Last time we ended with this wonderful cosmological model that we're all quite proud of. It probably explains the universe from a jiffy until today. It has these marvelous things, like the largest things in the universe starting out as subatomic quantum fluctuations, and it's got dark matter and dark energy, and it's, couldn't be more interesting, much more interesting than science fiction, and it's science fact. But it is built upon these 3 things, which do not occur in the standard model of particle physics, which provides, that's 200 years of reductionism, that's our knowledge of how the world works, and there is no dark matter, there is no dark energy, and there is no field, scalar field, that would give inflation. There is the Higgs field. I'm using the word field because you all know field because of the Higgs field. And so there was a provocative question, maybe, I can't remember who asked it, or maybe I even asked it, are we close to a theory, or are we just fooling ourselves with epicycles? And so these are 3 mysteries where I think we have a very good chance to solve them, or at least make progress. And if we do, then we can declare a golden age of cosmology. Okay, let me talk about inflation. And if you remember, it predicts that the universe is uncurved, or the jargon we like to use is flat. It predicts that the lumpiness arose from quantum fluctuations, and that plus the dark matter leads to this cold dark matter. And then I mentioned, and I'll talk more about it today, that there was another sneaky prediction there that I didn't say much about, is that the same subatomic quantum phenomena called ripples in space-time, that when they get stretched and let go, end up being gravitational waves, ripples in space-time that we can detect. And, well, I don't want to spend a whole lot of time on it, and some of these numbers I decided to go, instead of the PowerPoint version, a more colorful version. And remember, I'm a University of Chicago professor. We have at least one, actually, we have several University of Chicago graduates who know that there's no grade inflation, so these are serious grades. So I tried to, I went with this slide, so some of the numbers are not quite up to date, but this flat universe, that means omega equals 1, that means you find the critical density. And the number now is actually 1.005 plus or minus 0.006, so within 0.5%. And so I give that, oh yeah, I got a double plus for doing it the hard way. That was to remind me to say, remember, when we had stalled, and the astronomers in the audience remember this, they thought they had us, we had stalled at about 30%, because that's all the matter we found, actually more precisely 27 now. Then we pulled out of somewhere a hat. This is a PG audience. We pulled out of a hat dark energy. Yeah, we're not going to go any further than that on that one. And then the lumpiness from quantum fluctuations, and I'll show you that again. That's the curve with the acoustic peaks, and that really fits very, very well. And then cold dark matter we're going to take credit for, because once you specify the lumpiness and then somebody else tells you what the matter is, then you have a story, well, it's not even a story, it's a theory of how structure forms, and that gets a very high grade. And then finally, I want to focus on the gravity waves, because in some ways that's the smoking gun. And I just remind you here of the microwave background, which again, maybe there's some more pitter-pattering today. Do we have more cosmologists? So this really, it's a picture of the universe when it was very young, and very smooth but slight lumps. And if you do this mathematical operation and plot the right thing, what you get are these marvelous acoustic peaks, the ringing of the universe. And this curve is the prediction of the theory, and the points aren't just drawn on the curve, the points actually fall on the curve, and that's quite remarkable. And so we think we're on the right path with inflation. I am not only a booster of Chicago, you may have heard that from someone, but also inflation, but I don't think we're quite there yet. And, the cold dark matter, gosh, you could have a whole series talking about how this theory predicts how we built up the structure in the universe. And when I was a graduate student, or even when I was a young assistant professor, we were really struggling. We said, well, lumpiness plus gravity, it does something. And now we have a highly predictive theory that tells us where we should find the first stars, the galaxies, the clusters. It tells us what kind of large-scale structure we should have, the voids, the filaments. This is more technical, but it predicts quantitatively what the spectrum of lumpiness is. It predicts the properties of clusters, and it's really, if it isn't correct, if it isn't how nature really did it, it's an extremely good approximation. And so, oh, I got very excited here. So the status is excellent. I apologize for my exuberance. So the one thing that's missing that, and probably it's not politically correct to call it a smoking gun, is this a carry state? Anyway, so there's equations here, not for you to stare at, but what's spectacular about this is the density perturbations, the lumpiness, which we probed the best, we knew they had to be there, and we even knew the approximate amplitude. This we knew nothing about. This is bringing something new to the table. And secondly, if you can measure the gravitational waves, by this formula here, and all I want you to look at is seconds, it will directly tell you when inflation took place. And so T is just the, how strong the gravitational waves are, and the energy scale. But the main thing is just SEC is seconds. So if you measure them, you instantly know, because you'll notice that I told you when Big Bang nucleosynthesis took place. I told you when the atoms formed, but when I said inflation, I kind of segued to this joke about a jiffy. And so, by the way, a jiffy, that isn't a technical term. Anyway, so they'll tell us when inflation took place, and it might help us actually get to identify the correct theory of inflation. So how would we go about doing that? I have a diagram here, and we have this little pack that those of you who don't like diagrams, you view it as you would an impressionistic painting. So green, so that's the promised land of theory. And furthermore, and this is, there are two ways to detect the gravity waves. I'm going to tell you the best way to do it is to look at the microwave background. And so the other way to do it is to build a detector like the LIGO detector or some kind of gravity wave detector to directly detect them. LIGO are two detectors in the United States that were built by the National Science Foundation. And so this is just sensitivity. Unfortunately, all the imagined LIGO, which actually exists, and other imagined detectors have a sensitivity way over there, which means you can't get to the expected signal. And then this is the strength of the signal that gets impressed on the microwave background by the gravity waves. And this you can detect. So I'm just going to focus on this. So this is one of these hot spots on the microwave background. And it turns out, last night was a good reminder for it because we remember back in 1960, you know, the 5 o'clock shadow that Richard Nixon had when he was debating John Kennedy. And so it turns out that the hot spots on the microwave background have a 5 o'clock shadow, by which I mean the polarization. So I bet most of you know that light is polarized. And so it's not a hoax when they sell you those polarized glasses, that light comes in two different varieties, like this or like that. And so that's called the polarization vector. And there are different ways, different patterns of polarization. And the polarization vector is like the way the electric field points. So one pattern of polarization is called E. And it looks like this. And the other is called B. E and B. So it's very simple. And it turns out that the gravity waves, the lumpiness only excites this one. And the gravity waves excite both, but only the gravity waves excite the B mode. So why is that important? So T is the amount of gravity waves, S is the amount of density perturbations. Because only the B modes, only the gravity waves excite the B mode, you can detect the gravity waves even if they're very small, like 1/10,000th. And so this is a very good way to get at the gravity waves. Okay, so that's a goose. Only the bravest experimentalists, there are two words I'm not going to use today. One begins with J and the other begins with P. Only the bravest experimentalists will chase this wild goose because we don't know. This diagram keeps going. And so the value, the strength of the gravity waves could be incredibly small. We can't tell you how big it is. And I'll show you how hard these measurements are to do. And on the other hand, the payoff is enormous. If you detect them with that simple equation I showed up there, you know when inflation took place, and this is the smoking gun of inflation. So this is high-risk science. And so let me show you again, this is what's been done. So this is the E stands for the E mode. So the E mode has been detected. You'll notice the error bars are pretty big. And a lot of these experiments are Chicago experiments, Quad, CapMap, DAISY, SPT will be on there soon. So we've detected the E mode, and the E mode is very, very small. I'll get to how small it is. Here is the B mode, and for those of you who are familiar with science, the way we plot data, this doesn't mean there's a detection. This is an arrow saying it can be no bigger than this. And this is strength 10 to the minus 1. And if you remember the previous slide, it could be 10 to the minus 5, it could be 10 to the minus 6, so it could be very, very small. So right now, we don't know that much. And let me tell you the temperature units over here that you have to measure. This is what the curve would look like. This is what you're hoping to find if the strength is 10 to the minus 1. That's a nanokelvin. So these are very, very hard experiments to do. And, but the payoff is very, very, very big.